Hi everyone, today we're going to talk about absolute dating. So let's say you have a rock sample, and now you want to know exactly how old that rock is. There are a couple of ways you can do that, and that's what we're going to talk about today. The first thing we need to talk about is something called a zircon, because zircons are really special minerals that can help us figure out exactly how old certain rocks are. So a zircon is a type of mineral that exists as tiny crystals that are extremely hard and durable, so they're going to last a long time. They can survive erosion, they can even survive metamorphic processes. Inside a zircon crystal, uranium, the atom, will naturally decay to lead over millions or even billions of years. So if you can measure how much uranium is left compared to how much lead has been formed, you can actually determine how old that zircon is. Think about this. If you date a zircon crystal that you find in a sedimentary rock, are you actually dating how old the sedimentary rock is? Well, sedimentary rocks are made of sediments that came from other rocks, so no, you're only dating the sediment that made up that sedimentary rock. What about a metamorphic rock? Well, again, no, metamorphic rocks are made from pre-existing rocks. So it's not going to tell you how old the metamorphic rock itself is. Finally, what if you find a zircon in an igneous rock and you date the zircon and find that it's 1 billion years old? Bingo, you've dated how old the igneous rock is, and you know exactly when that igneous rock was formed, because igneous rocks are formed from cooling magma, and that magma crystallizes. So, elements can decay and turn into other elements. Yep, this is a totally natural process and it's called radioactivity. We need to take a tour inside an atom to understand a little bit about how radioactive decay works. Neutrons and protons exist in the nucleus of an atom. The number of protons in the nucleus tells you the type of atom that you're dealing with. If you change the number of protons, you change the atom that you're dealing with. An atom of any given element can have a different number of neutrons in the nucleus. That just changes the mass of a single atom. It doesn't change the element. It doesn't even change how that element reacts chemically. Here are 3 examples. Here we have a lithium atom, 3 protons means it's lithium, with 4 neutrons in the nucleus. Here we have a lithium atom, but with 5 neutrons in the nucleus. These are isotopes of each other, and it's totally normal. Here, we have a lithium atom, but it's just missing an electron. This is actually called an ion. All 3 of these lithium atoms will interact in a very similar way when it comes to chemical reactions. The other thing you need to know is that not every single nucleus is stable. In fact, of the 2,500 known nuclei, less than 300 are actually stable. So if a nucleus is unstable, it's going to eject particles and radiation in an attempt to become more stable. So I want you to think about all of those protons and neutrons that are glued together in the nucleus. The number of protons and neutrons doesn't always create a nucleus that's going to stick together very well. Sometimes it will need to become more stable by throwing off certain particles and radiation. Here's an example. Potassium in bananas is naturally radioactive. Not that much, so it's safe, but it is radioactive. If a nucleus ejects particles or radiation in order to become stable, and in doing so, the number of protons in its nucleus changes, then the element itself has changed. So the new element that forms is typically called a daughter product. One of the ways in which potassium-40, which exists in bananas, can decay is through a process called beta- decay. Potassium-40 has too many neutrons in the nucleus, which makes it a little bit unstable. So when it decays, one of those neutrons can sometimes turn into a proton, which stays in the nucleus, as well as an electron, which gets ejected from the nucleus, along with something called an electron antineutrino. So the next question is, if we know the nucleus of an atom is unstable and we know it's going to decay, how do we know when it will decay? Well, in order to model this, we need to determine the isotope's half-life. That means, how long does it take on average for half of the nuclei in a sample to decay? So here are some examples. The first one we're going to talk about is carbon-14. Carbon-14 is an isotope that exists naturally in organisms' bodies. So you're full of carbon-14 right now. But it's constantly getting recycled in an organism's body due to the natural chemical reactions that happen in every organism. So once an organism dies, then whatever carbon-14 was left stays there, and over time it will decay. When it decays, it undergoes beta-minus decay, just like our potassium-40 example. An electron is ejected from the nucleus, an electron antineutrino is also ejected, and what's left is actually nitrogen-14. Now, carbon-14 decays to nitrogen-14 with a half-life of 5,730 years. So if an organism dies and that organic material is able to stay around for a really long time, in 5,730 years, half of the carbon-14 in that organism's tissue will have turned into nitrogen-14. So if you can measure how much nitrogen-14 you have compared to carbon-14, you'll actually be able to know how old that dead organism is. Another example is rubidium-strontium. Rubidium-strontium decay is another common example. This decay has a half-life of 4.92 times 10 to the 10 years, so quite a bit longer than carbon-14. Uranium is a very common example for dating rocks. Uranium will decay through a whole bunch of steps and eventually will turn into lead-206. So uranium-lead dating is one of the best and most accurate methods for dating rocks, specifically for dating those zircon crystals. It has a very long and convoluted decay chain, and it looks like this. Uranium, thorium, protactinium, all the way down through a convoluted process until you get to lead where it's stable. Now, not every single unstable nuclei will decay the same way. For example, potassium-40 can undergo beta-minus decay. So one neutron in its nucleus will turn into a proton, shoot off an electron, and turn into calcium-40. That'll happen 89% of the time. Calcium-40 is more stable than potassium-40. 11% of the time, it'll go through a slightly different process, and it will eventually become argon. Argon is also more stable than potassium-40. Here's the interesting thing about argon, though. It's a noble gas, so argon will not form chemical compounds. If you have a sample of rock and there's argon present in it, the only way it got there was through the decay of potassium-40. If you know the half-life of potassium-40 and you know how much argon was present, you can determine the age of the rock. Let's say we start with a certain number of nuclei. Let's call this number N0. If we want to know how many nuclei we have left of our original material, a certain time later on, let's figure that out. After one half-life, we will have exactly half the nuclei that we started with. So in one single half-life, we'll have 1/2 of N0, the original number we started with. After 2 half-lives, we're going to have half of this number. So half of the number of nuclei we started with. That's equal to 1/2 squared times N0. After 3 half-lives, we're going to have half of this left over. That's half of our original number of nuclei, which is the same as 1/2 cubed times our original number of nuclei. Do you see a pattern yet? It's always 1/2 raised to the exponent of however many half-lives have gone by times the original number of nuclei. So here's the equation. If I want to know how many nuclei I have left over, N, it's equal to N0, my original number of nuclei, times 1/2 raised to this exponent. T is the time that has elapsed. T 1/2 just represents the half-life of that particular sample. Here are some half-life values for a variety of unstable isotopes. For example, uranium-235 we talked about already. It has a half-life of 7 times 10 to the 8 years. Carbon-14, we talked about that as well, has a half-life of 5.73 times 10 to the 3 years. We can look at some that decay very quickly as well. Beryllium-8 has a half-life of 2 times 10 to the minus 16 seconds, so this one's barely around at all. You can have a look at this table for some other examples as well. Here's a graph that shows exactly what that equation that we just came up with is telling us. After one half-life, here, 50% of our sample remains. After 2 half-lives, half of 50% remains. That's 25%. After 3 half-lives, half of that remains. That's 12.5%. Here's an example where we're going to solve a problem involving radioactive decay. So we have a sample, and let's say this sample contains 1 times 10 to the 22 carbon-14 nuclei initially, and we want to figure out how many will be present after 13,500 years. So this number here is our original number of nuclei. So in our equation, that's N0. The half-life of carbon-14 is something we can actually find on this table. So we look for carbon-14, there it is, and the half-life is 5,730 years. Now we're also given T, the total time that has elapsed. So here are our givens in the problem. We've got a total time of 13,500 years, and we've got a half-life, T a half, of 5,730 years. We're going to use this equation, and we're going to substitute in everything that we know, and all we have to do is solve for n. So we plug in our original number of nuclei. We've got 1/2 raised to this exponent. Make sure that you calculate this exponent first. It'll make your life a little bit easier. You want to figure out how many half-lives have elapsed. That's 13,500 divided by 5,730. You will end up with 1.95 times 10 to the 21 remaining nuclei of carbon-14. Here are some other types of absolute dating that can come in handy. If you want to know how old something is that hasn't been dead for that long, you can always look at tree rings. Tree rings are a nice way of determining what possibly happened in the recent past. Every single year, the organism will grow, and that means the tree will leave different rings on its inside, concentric circles that will tell you whether the tree grew a lot that year or not that much. So if you count tree rings, you can actually count back in time. Interestingly, dendrochronology, which is the science of counting tree rings, can date a piece of wood back several thousand years. Something similar can be done with ice cores. So you can use a drill to extract an ice core, which could have accumulated over hundreds or even thousands of years. Different layers in an ice core represent snow accumulation seasonally, or if you have really deep compacted layers over several seasons. But again, this is the act of counting back in time to determine an absolute age when something happened. Finally, you can have something called varves. Varves are very similar in concept to tree rings and ice cores in that you're counting back in time layer after layer. Except varves involve sediment that's deposited layer on layer. If you compare the different layers of sediment consecutively, you can put a chronology in place. Keep in mind, this one's a little bit dicey because if you have some erosion, if the sediment gets churned up and you miss a couple years, it could be less accurate.